Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to lecture number 28 on the subject of computer organization and assembly language programming. The title of today's session is Programming Model of x86 Architecture. Well dear students, the programming model of a microprocessor contains a concise description of the programmer visible registers and their functions. So here is the agenda of today's session. Well, instead of straight away jumping on the memory model and register set of x86-64 microprocessor, we will go step by step. We'll start with Intel 8080, then 8086, then 8386, and then finally we will see and understand the memory model and register set of x86-64 microprocessor. So we have a lot to do today, so let's start playing. Let's start with Intel 8080, which was launched in 1974, having 8 bits data bus and 16-bit address bus. Well, in Intel 8080, they used the flat memory model, also called the linear memory model, which refers to a memory addressing technique in which memory is organized in a single, sequential, and contiguous address space. The addressing is simple. You simply put a 16-bit address on the address bus and you get back the 8-bit value stored at that address. And please do note that there is no necessary relation between the number of address lines in the memory system and the size of the data stored at each location. 8080 stored 8 bits at each location, but it could have stored 16, 32 or even 64 bits at each location and still have a 16-bit memory address line. So let me put it in simple words. This Intel 8080 microprocessor could address 64 K locations, with each location having 8 bits of data. Well, in 8080, the program, stack and data occupy the same memory address space. The program can be located anywhere in this memory. The jump, branch and the call instructions use 16-bit addresses. So a program can jump anywhere within this 64 kilobytes of main memory. The processor uses 16-bit addresses for this data memory, so the data can be placed anywhere within this 64 KB. And similarly, the stack memory is also limited with the size of the memory, that is 64 KB bytes. And of course, in 8080, the stack grows downward from the higher address towards the lower address. Well, as far as the register set of 8080 is concerned, there is an 8-bit A register, the accumulator register, used for arithmetic, logic, I/O and load store operations. Then we have 6 general purpose 8-bit registers, B, C, D, E, H and L. This B, C, D, E and HL can be used in pair by programmer as 16-bit data pointers to reference the memory addresses. Well, this stack pointer SP is a 16-bit register pointing to the top of the stack, and this IP instruction pointer is also of 16 bits and always points to the next instruction to be executed. Then we have the flags register, 8-bit flags register, having 5 status flags. 1, 2, 3, yes, 5. Well, these flags are modified automatically by the CPU after an arithmetic or logic operation. Bit 0 contains the carry flag. It holds the carry out after addition or the borrow in after subtraction. And this carry flag is used to identify an unsigned overflow. This bit number 2 contains the parity flag. You all must be knowing that parity is the count of 1 bits in a number expressed as odd or even parity, represented by a 0 or 1 respectively. Well, dear students, in early processors, this parity was used for checking data in data communication environments. Today, parity checking is accomplished by data communication equipment instead of the microprocessors. So this parity flag is not much of usage these days. Bit number 4 contains the auxiliary flag. It holds the carry out after addition or the borrow in after subtraction between bit position 3 and 4 of the result. In early processors, auxiliary flag was used in BCD arithmetic. This flag is also not of much usage in today's microprocessors. This bit number 6 contains the 0 flag, ZF. It is set by the microprocessor if the result of an arithmetic or logic operation is 0. Bit number 7 contains the sign flag. It holds the most significant bit, or you can say the sign bit of the result after an arithmetic or logic instruction. Okay, so with the brief intro of these flags, let me talk about the instruction. My dear students, this Intel 8080 support a variety of data movement, arithmetic, logic, control transfer, and I/O instructions. It has a support of just 4 addressing modes: immediate, register direct, and register indirect. Well, dear students, we are not going to write 8080 assembly programs, but I thought it appropriate that we should start our discussion with the programming model of 8080 to have a fair idea as to how intelligently the Intel designers progressed with the design architecture of Intel CPUs, and thus ensured the portability of old programs on every upcoming CPU design. Okay, so now let's move on to 8086, which is the foundation of all Intel's future x86 architecture. It was launched in 1978 and was a processor with 16-bit data bus and 20-bit address bus. Okay, so Intel 8086 has an addressable memory of 1 megabytes, which is 16 times more than Intel 8080. The designers of 8086 wanted that all the assembly programs running on 8080 should also run on 8086. And to make this porting possible, the designers of 8086 divided its 1 M memory in 64K segments, so that the previously written programs in 8080 could be loaded into any one of the 64 KB byte memory segment and can execute successfully. Well, the newly written assembly programs for 8086 could use the entire 1 megabyte of memory address space, and in contrast to Intel 8080's flat memory model, this is known as the segmented memory model. And a segmented memory model divides the entire memory into groups of independent segments referenced by pointers located in special CPU registers called the segment registers. And another argument that come in favor of a segmented memory model is that the three logical parts of a program, namely code section, data section, and stack, can appear as three distinct units in memory. And this division was not possible, of course, in the flat memory model that was there in 8080. Okay, dear students, now let's talk about the register set of 8086 microprocessor. So there are four 16-bit general purpose registers, AX, BX, CX, and DX. If being an assembly programmer you want to access the lower 8 bits of these registers, you can use the names AL, BL, CL, and DL. And similarly, if you want to access the higher 8 bits of these registers, you can use the names AH, BH, CH, and DH. Well, this AX is called the accumulator register, used in arithmetic, logic, and data transfer instructions. For example, in multiplication operation, one operand is stored in this AX or maybe in AL according to the size of the operand. Then we have the BX register. This is called the base register, usually used for based indexed addressing. We will talk about this in some future session. This CX is called the counter register, normally used to store the loop count in iterative operations. This DX is called the data register, normally used to hold part of the result from a multiplication or part of the dividend before a division operation. And this is also used to store port numbers in I operations. So after these four general purpose registers, then we have the special purpose registers. And first of all, Intel 8086 has these four segment registers, 16-bit segment registers, and each containing the starting address of a memory segment. This CS, code segment register, stores the starting address of the code segment where program instructions reside. DS, data segment register, stores the starting address of the data segment where both initialized, uninitialized data and constants reside. SS, stack segment register, stores the starting address of the stack segment where all the local variables and function stack frames reside. ES, extra segment register, is an additional data segment that stores the starting address of the extra segment. Well, other than the data segment, this extra segment is used for data as well as for pointers, and this is mostly used by some of the string instructions to hold the destination data. Well, after these four segment registers, we have five special purpose registers. The stack pointer register and the base pointer register, both relate to the stack segment. You can say that the SP, stack pointer, points to the current top of the stack, and this BP, base pointer, points to a fixed location within a function stack frame. This SI, source index register, is used as an offset relative to the data segment, also used as a source in some string related operations. This DI, destination index register, is used as an offset relative to the extra segment, also used as destination in some string related operations. Finally, this famous IP, instruction pointer register, is used as an offset relative to the code segment. It always contains the 16-bit offset of the next instruction to be executed inside the code segment. In the upcoming slide, of course, I will show you the exact relation between these segment registers and their corresponding offsets. And finally, we have the flags register again. Well, dear students, in 8080 the flags register was of 8 bits having 5 status flags. This carry flag, parity flag, auxiliary flag, zero flag, and this sign flag as well. In 8086 the flags register is of 16 bits having 4 additional flags. 1, 2, 3, 4, yes, 4. A status flag called the OF, overflow flag, at bit number 11. It is set in case of a signed overflow. 2 system flags, the trap flag at bit number 8, used to enable a single step mode for debugging. Interrupt flag at bit number 9 to enable or disable external interrupts like keyboard. And finally, there is a control flag as well called the direction flag at bit number 10, used for moving or comparing string data. When this direction flag DF is 0, the string operation takes a left to right direction, and when this DF flag is 1, the string operation takes right to left direction. Okay, so this was for the flags register of 8086. Let us spend some more time on understanding as to how the segmented memory model of Intel 8086 actually work. We have a data section. This is the data segment, this is the code segment, this is the stack segment, and this is the extra segment. These are the 4 segments, 64 KB each, and overall, of course, this is the 1 megabytes of memory, addressable memory by 8086. My dear students, other than porting 8080 assembly programs on 8086 processor, another big advantage of segmented memory model is that it allows the 16-bit instruction pointer register to address a 20-bit memory address space. Naturally, this address will be of 20-bit. So how come a 16-bit instruction pointer can point to this 20-bit address space over here? So this is one of the biggest advantage of segmentation. And the segmentation is a process in which the main memory is logically divided as shown over here into different segments, and each segment of course has a starting address of its own. You can see if the addresses are starting from here, this is a base address of the data segment, this is a base address of the code segment, this is a base address of the stack segment, and this is a base address of the extra segment, and this is what is shown over here inside the arrows. So the DS register contains the base address of the data segment, CS register contains the base address of the code segment, SS stack segment register contains the base address of the stack segment, and ES register contains the base address of the extra segment. Now $100 question that might come to your mind is that how a 20-bit address is stored in a 16-bit segment register. How come these 16-bit segment registers can contain a 20-bit address? Well, the answer is every segment begins from an address where the lower 4 bits are 0. That is, the address is exactly divisible by 16. And we do not store the lower 4 bits of the address in the segment register. So the segment register has a 16-bit, upper 16-bit of the address, and the lower 4 bits are assumed or implicitly assumed to be 0. And this 16-bit boundary is often called the paragraph as well. So my dear students, these 4 segment registers, data segment register, code segment register, stack segment register, extra segment register, holds the upper 16 bits of the starting or the base address of the respective 4 memory segments. Moreover, in 8086, the minimum size of a segment can be of 16 bytes and maximum can be of course 64 KB. This data segment register points to the starting address of this 64K data segment, and this SI or the source index register is used as an offset within the data segment. Since this SI is of 16 bits and this can address a 64K memory, so it can start from this starting address of the data segment and can move up to the last address, that is the 64K address. So this SI, which is of 16 bit, can easily contain the 16 bit offset within this data segment register. Similarly, this ES register points to the starting address of this 64K extra segment, and this DI or the destination index register is used as an offset within this extra segment. And for the stack segment over here, SP or the stack pointer register points to the top of the stack, and this BP or the base pointer points to the fixed location within the current function stack frame. And finally, over here, the famous IP register or instruction pointer, it points to the offset within the code segment where the next instruction to be executed resides. Now, my dear students, another $100 question is, how a 20-bit address is stored inside this 16-bit offset register? Or let me rephrase my question. How to compute the 20-bit physical address from these two 16-bit addresses, one in the, let's suppose, the code segment register, and the other, let's suppose, in the corresponding offset register, that is IP. So let me explain this with the help of an example. Suppose the 16-bit code segment register contains 3F2A in hex, and the 16-bit IP register contains 1B08 in hex. So given these two values, which are normally given at times in this notation, CS:IP as well. So given these two 16-bit values, how can we convert them to a 20-bit value? Excuse me. So this is the formula that do all the magic, and we know that all the segment register contains the upper 16-bit of base address of the respective segment. So we multiply it with the 10 hex, or place 4 zeros on the right by left shifting the contents of the segment register by 4, and then we add the 16-bit offset, which in this example are the contents of IP register. So this is how we get the 20-bit physical address, which comes out to be 40DA8 in hex. My dear students, this is also known as real mode addressing, which uses a segment register, rather a segment address plus an offset address, 16-bit each, to make a address of 20 bits. Moreover, this diagram pictorially describes as how a 16-bit logical address is converted or translated to a 20-bit physical address. You can see this is the segment register, 16-bit segment register. We have placed 4 zeros on the right. This is the offset, appropriate offset of the appropriate segment. We add these two numbers, sum them up, and we get a 20-bit physical address, and this is what we have done in the calculation over here. Okay, so this slide shows the ALU over here, the register file over here, the control unit, and the data paths and memory connectivity of x86 processor at quite an abstract level. Well, my dear students, the 8086 CPU is organized as two separate processors called the bus interface unit BIU and the execution unit EU. Excuse me. The main task of this bus interface unit is to generate memory and I/O physical addresses for transfer of data between memory and this execution unit. The main task of this execution unit or EU is to execute the instructions and data received from BIU and store the result finally inside the general purpose register. Remember, dear students, this EU has no direct connection with the outside world. It receives and outputs all its data through this bus interface unit. And let me take this opportunity to describe the fetch cycle of this 8086 processor. And once again, let us suppose that 3F2A, this 3F2A is the starting address of the code segment, and if I place a 0 over here, 3F2A0 will be the 20-bit starting address of the code segment, and this 1B08 is the 16-bit address of the instruction within the code segment. This adder unit inside the BIU will add the two values of the code segment register and the IP register given to it, and will generate the 20-bit physical address of the memory, will fetch an instruction. Of course, this is a code segment, so that will contain an instruction. Fetch an instruction and place that instruction inside this 6-byte prefetch instruction queue, which works on first in first out principle. And why 6 bytes prefetch instruction queue? Because in x86 instruction size varies from 1 byte to 6 bytes. Well, this execution unit draws an instruction from this prefetch instruction queue. This control unit checks for the instruction opcode and the operands, and I think you know what are opcodes and operands, delivers them to the ALU, which carry out the required arithmetic or logic operation and writes the result in appropriate destination registers, and also updates the bits of the appropriate bits of the flag register. My dear students, while this execution unit is executing an instruction, this bus interface unit proceeds to fetch a new instruction, and depending on the execution time of the first instruction, this BIU may fill this prefetch instruction queue with several new instructions, and before the EU is ready to draw the next instruction. I think this is enough of description. Please, if you have still ambiguities regarding how the 8086 processor fetches and executes the instruction, please rewind this part of the video and see it again. Otherwise, you can visit me during the counseling hours. So let me move ahead. Well, my dear students, Intel 8080 assembly programmers were very happy as all their programs were successfully ported to Intel 8086 machines. The problems began after a few years when programmers who had never seen the 8080 processor started to write new programs from scratch for 8086 processors. Well, these 8086 programmers actually do not need the segmented memory model, but have to forcefully use it. Programs that need to access large data structures larger than 64K of memory at a time had to use memory in chunks of 64K, and switching between chunks by switching values into and out of the segment registers, which was of course a tricky task at that time. Therefore, people say that segmented memory model was a wise short-term thinking but catastrophically bad long-term thinking. So anyway, then came the turn of the next processor, Intel 8386 microprocessor, which was launched in 1985. So my dear students, 8386 had a 32-bit data bus and 32-bit address bus, capable of addressing 4 GB bytes of main memory. And it also introduced the concept of protected mode, paging, as well as virtual memory. Well, Intel 8086 has an address bus of 20 bits and therefore can address a physical memory of 1 megabyte. On the contrary, Intel 8386 has an address bus of 32 bits and therefore can address a physical memory, of course, up to 4 GB bytes. To ensure portability, once again, Intel introduced protected mode of memory addressing in 8386 and named the older memory addressing scheme of 8086 as real mode. So finally, in 8386 we have two modes. One is known as the real mode and the other is known as the protected mode. Let's talk about them one by one. In real mode, irrespective of the total available memory, only first 1 M of memory can be accessed. To translate a logical address, this is a typo, to translate a logical address to a physical address, that is segment offset addressing is used, and that I have discussed in detail on the previous slide. This is the new mode of 8386, that is protected mode, and this allows access to data and programs located above the first 1 M of memory, called the extended memory. And of course, at the same time, it also allows to access the first 1 M of memory. The segment registers are now considered part of the operating system. You can neither read nor change them directly. They point to OS data structures that contain information to access a location. We'll talk about this in a short while. And of course, 32-bit protected mode support much larger data structures than the real mode. Okay, so my dear students, this slide shows the overall address translation process of the 8386 processor. You will go into the details of all this when you will be studying memory management in your operating system concept course, inshallah. Over here I just want to highlight that unlike the segment offset addressing of real mode, this is a bit different. Here you can see the 16 bits of the segment register. That can be the code segment, data segment, stack segment, and so on. And this does not contain the base address of a segment, rather contains a selector that selects an 8-byte entry from our descriptor table, which can be a global descriptor table or a local descriptor table. And each entry contains information like the starting address of the segment, its size, type, and permissions. And finally, over here, the 32-bit offset, for example, the contents of IP register or maybe some other pointer, allows the microprocessor to access data within a segment that can be up to 4 GB byte in length. Since the segment and offset register are very much in the picture, so protected mode is quite identical to real mode. In fact, most programs written to function in 8086 real mode will function without change in 8386 protected mode. Moreover, switching to protected mode is easy. You just need to set a single bit in a control register of the CPU. And dear students, before I move ahead, let me give you the summary of the memory model of the three processors that we have discussed so far. In Intel 8080, we had the 16-bit address and used a flat memory model in which we convert one address value into its corresponding physical address value directly. Then in 8086 we had a 20-bit address and used a segmented memory model in which we convert two address values into its corresponding physical address value. And over here in 8386 we of course had a 32-bit address, and we also use a segmented memory model. As you can observe over here, we have the 16-bit selector. The segment register is called the selector over here. So this 16-bit selector and this 32-bit offset, they together combine to convert it to the physical address. This 16-bit selector is used to index the descriptor table, local or global, which with other important information contains the base address. And this offset register is then used to do all the paging thing, the page directory and the page table and the offset within the page table and so on, and then finally we reach to the physical address. So this is how the 8386 maps the 32 plus 16, maybe 48-bit logical address to the physical address. Okay, so I think enough about memory. Let us talk about 8386 registers now. Okay, so all the 16-bit data registers of 8086 are extended to 32 bits and named as EAX, EBX, ECX and EDX. Well, this EAX register is addressable as EAX if you want to access all the 32 bits. Maybe AX if you want to access lower 16 bits, AH if you want to access the higher byte of AX, and AL if you want to access the lower byte of AX. And the same is true for EBX, ECX as well as for EDX. The 16-bit pointer registers of 8086 are also extended to 32 bits and named as ESP, EBP, ESI, EDI and of course EIP. Well, there is no change in the size of the segment registers, however their count is increased. So in 8386 there are 6 segment registers of 16-bit each. After this ES, that is the extra segment register, the two new segment registers are named as FS and GS and can be used for both data encode. Finally, the 16-bit flag register of 8086 is also extended to 32 bits over here and named as E flags. In 8086 there were a total of 9 flags, and in 8386 we have 14, that is 5 new flags were introduced. This IOP0 and IOP1 at bit number 12 and 13 are 2 flags that are used in protected mode to select the privilege level for IO devices. This stands for, I think, input output privilege level 0 and 1. So this NT flag at bit number 14 is the nested task flag, indicating that the current task is nested within another task. RF is the resume flag used in debugging, and this VM is the virtual mode flag. Okay, I think enough for 8386 registers. Let's move ahead. Okay, so dear students, finally, in 1997, Intel launched the P6 microarchitecture, also referred to as the 8686 architecture, and later in 2003, the famous x86 64 architecture was launched together by Intel and AMD. Well, it was a 64-bit architecture along with many other new features which are not of our concern right now. We have talked about these in the previous session. Well, my dear students, the x86 64 architecture defines three general modes for memory: the real mode, the protected mode, and the long mode. Well, real mode is a compatibility mode that enables the CPU to run older real mode operating systems and softwares like DOS, that is a disk operating system, Windows 3.1. In real mode, the x86 64 CPU works just like an 8086 and supports a real mode flat model and real mode segmented model. Protected mode is also a compatibility mode that enables the CPU to run older operating systems like Windows 2000, XP, Vista, and Windows 7, and of course their applications. In protected mode, the x86 64 CPU works just like an 8386 CPU. And finally, long mode. This is a true 64-bit mode, and this is where the x86 64 CPU is in long mode. All the registers that you get are of 64 bits, and all machine instruction also act on 64-bit operands. All 8386 registers, of course, are available, rather they are extended to 64 bits in width. My dear students, since we are going to write the assembly programs on Linux, here is the logical address space of a process running on a Linux-based machine. The memory layout for our process is divided over here into four main sections: logical sections. First of all, the code or the text section that starts from address 04, this 400,000, not from exactly 0. And above this code section we have the data section, and we have two parts of the data section: the initialized data and the uninitialized data. Well, this uninitialized data contains the statically allocated variables which are not actually initialized within the code. And above this data section we have the heap. And you all know that heap is a dynamically resizable region of memory which is allocated to a process on request. And in C or C++ you might have used the malloc and the new operators for using heap area. In x86 64 Linux, this region can grow to very large sizes, and the limit is imposed by the sum of physical memory and swap space. And finally, the fourth logical portion, that is the stack. The stack is used for keeping track of function calls, parameters, local variables, and of course return addresses. Well, on Linux systems, the stack size is typically 16 megabytes. Given the top of the stack as this 7FFFFF and so on, there is 7 and then we have 11 Fs. It grows towards lower addresses. This 16M is not a large amount of space, but as long as the programmer avoids putting large arrays on the stack, it serves the purpose quite well. Well, x86 64 CPU chips that you can buy today implement a 48-bit logical address, not 64-bit. You can see we have a 48-bit address over here. So it uses 48-bit logical address for virtual memory or the logical layout of the memory, and 40 bits for the physical memory. And I think 2 raised to power 40 or 1 TB byte or 1000 GB byte is quite enough memory for today. Well, why they have not used the 64 bits for the physical memory when the address bus is of 64 bit? Well, actually the chip makers, I think, have tried to save the transistors on the chip to manage the additional address lines for the time being. And this is how the 64-bit logical address is broken down into different fields used to translate this logical address into a physical address. Just note that the upper 16-bit are unused, so we have a logical address of 0 to 47, that is 48-bit logical address. How this logical addressing is converted to the physical addressing, this translation process is beyond the scope of this course, and inshallah ta'ala I'm hopeful that you will study this in your operating system course. So let us move ahead. Okay, so this is the register set of x86 64 microprocessor, for which we have been setting the stage right. Note the size of the general purpose register is increased to 64 bits now, and the count has also increased to 16. Also note the new naming convention of the registers over here, R0, R1, R2 and so on to R15. And of course, to maintain portability and to access data elements of sizes less than 64 bits, that is 32 bits, 16 bits and 8 bits. The lower portion of the registers can be accessed by using different names. For example, to access the lowest 8 bits of this register R9, suppose we want to access the lowest 8 bits of register R9, we will use the name R9B, B for byte. And to access the lowest 16 bits of this register R9, we will use R9W, W for word. And to access the let's suppose lowest 32 bits of this register R9, we will use the name R9D. This is a typo, this is R9D. You can use the same naming convention for these first 8 registers as well, or you can use the 8386 naming convention, that is this RAX, EAX, AX and AL and AH as well. One more thing I want to highlight is that for the first 4 registers RAX, RBX, RCX and RDX, bit number 8 to 15 can be accessed with AH, BH, CH and DH names, which are not shown over here. Okay, so the instruction pointer, this is the same, that was of 32 bits in 8386, now it is of 64 bits and named as RIP. And now a $100 question is, with the 64-bit of address and address bus, do we need these segment registers? Well, as I have already said before, that most 64-bit CPUs today can address something like 40 bits of physical memory, that is around 1000 G of memory. Who need more RAM than this? So the conventional reason to add segment registers vanishes, that is accessing a 20-bit memory using 16-bit address. And over here we have 63-bit address and we are just accessing the 40-bit address of the memory. So to my mind, in 64-bit programming, these segment registers do not have much role to play. Okay, so finally we come on to the flags register. So the 32-bit flag register of 8386 is also extended to 64-bit and renamed as R flags. You can just see 4 more flags that I have mentioned over here. what are the flags? We have the bit number 18 alignment check flag, bit number 19 virtual interrupt flag, bit number 20 this VIP or virtual interrupt pending flag, and that at bit number 21 the ID flag, identification flag. And still till date the lower 32 bits are being used, so once we will be using Linux on our 64-bit machines, you will mostly see the name E flags over here in your debuggers. And finally we have dedicated registers to support the floating point and the SIMD and SSE instructions. SIMD means single instruction multiple data, and these SIMD instructions allow a single instruction to be applied simultaneously to multiple data items, and they normally used these registers, 128-bit registers, XMM0, XMM1, XMM2 and so on to XMM15. Well, new processors also provide streaming SIMD extensions that use these 256-bit registers, namely YMM0, YMM1 and so on to YMM15. My dear students, we will inshallah see all these registers in action when we will be making our hands dirty by writing and executing assembly programs for our x86 64 systems. Okay, so that is all for today's session. I've tried my best to give you all a detailed overview of the memory model as well as the register sets of 4 microprocessor architectures: Intel 8080, 8086, 8386 and x86 64. I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning and Allah Hafiz.